that the dead cells resurrected. Okay, it is very tough. Rather, other areas of the brain cell will take the role and will learn the new functions to do it. So it takes time to teach the brain cells to do the new jobs. That's the rehab, kind of. So of course, we can have the human therapist and help that now you learn how to walk, you lost the function, but you need to coordinate it, the gait cycles, that's the part of it. But recently, in the physical therapy now using the brain-computer interface, and she's wearing EEG cap that connects to the rehab robot. And now, not the human therapist move her arm to teach, and the coordination between the muscles and with the brain. Now what? The robot teach that. Not the passive way, it is what? Active way. Because she wants to move her arm. And that will trigger certain area of her brain, work hard, right? And eventually this will move, and that area will have the acceleration in the learning process. That's the hope in the physical therapy. So the BCI is one of the very popular the items in the physical therapy area because of the stroke. Okay? So we actually work with some of the physical therapy, the faculty members, and to make this kind of a device. More tough case than the stroke, but still very popular. The applications of the brain-computer interface treatment is spinal cord injury. I think you recognize this person, right? Christopher Reeve, right? Okay. It was the unfortunate, the instant, but while the horse riding, he fell and got the spinal cord injury, and he lost the complete motion under the neck. So that's what happened. He passed away. The issue of this problem is that, as you know, you remember that for the muscle control, there is what? Highway. That's the spinal cord. Got broken. So what if you have the issue in the Highway 5, and you want to go to the Carlsbad from the SSU, and the Highway 5 is disconnected? What do you do? Yeah, you go 15, and you may take the 78, right? Obviously, and it might be the way to do. So you take the detour. Creating the detour, artificial way, is what we do. So how do we do? We take the information. It's supposed to go through the Highway 5, but take the information, and the information will be processed by the machine, and will bypass the what? The disconnected highway, and then what? Send the information to the area or the nerve that control the muscle. So bypassing the discontinued and the highway is the usual the approach of using the BCI. Very hot area, and now we are seeing some success of it. Okay? So now let's get into the BCI, brain-computer interface. BCI, we need the information from the brain. And what information? Action potential, the spike. Actually, it is very, very weak signal, and each individual neuron generates that. So there are 100 billions of the neurons. There are so much of the information coming out, right? So the most accurate way to do is that actually you have a electrode or very, very sharp needle and put that one inside of your brain, and then measure what? Electrical signal. So put the chip inside of the brain. Or we put not inside of the brain, but top surface of the brain, but under the skull. That's partially invasive. Or we will have that just top of the skull, which will be most the safe way of it. But we'll get into that, the pros and cons. But eventually the signal will be digitized. We'll go to the computer and doing the signal processing, and then creating the pattern recognition and translation, eventually change to the commands and to the device. Either you can do the communication with the computer, and or you can have environmental control, and or you can actually have the movement control of the robotic prosthetics, so that for amputee, the patients can move his arm and with the robotic hand. Or we can have smart vehicles, and including the wheelchairs or the vehicles. Or I mentioned that to you, we can have very smart way of the neuro rehabilitation for the stroke patients or Parkinson patients or and so on. So this is the BCI. This is very, very difficult to work because it handles the human. And it handles the brain. And no one will open his or her skull and donate it, right? While he or she is alive. So it is tough, extremely tough to do. So, but that's the premise. We need to tap the electrical signal from the brain, and we need the signal processing in real time, and we do the intended the control through the control system, and then usually we have the feedback and through the 5 senses of the human, and then the 5 senses goes back to the brain through the certain strip of the brain, and then it generated the signal, and we tap the signal, for example, motor strip, we process it again. If we have that complete feedback, and now we have what? Mobile disorder would be solved. Probably the one who has an issue in the gait cycle because of the stroke might be able to walk, because we can generate the right signal to the certain the muscles in the thigh and the shin, so that the patients can walk and actually understand the rhythm, so that a bipedal work completely. That is hope. But getting the signal, the electrical signal that I have mentioned, is not trivial. And of course, the most invasive way is look like that. It looks dangerous, right? Yes. It is very, very sharp needle. It's about size of a 5 millimeter by 5 millimeter, about 1 millimeter, and tall. The really sharp needle, but those are all electrode array. Most popular one is from the University of Utah, so we call Utah array. That's the most popular one. And actually, we put that into the brain. Oh, would it be painful? No. You know that, right? Wouldn't be painful. So yeah, that's what.
Painful to think of it.
But it is a very tough way, because it leaves the damage, scar. More than that, and the human has a defense mechanism. So the actually conductivity of the needle goes lower, 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 so the functionality fades away. So what do? You have to reopen the brain, replace it, make it another scar, you know what I mean, right? It's tough issue. So a little bit easier on the human, the brain is a little bit less invasive. Just put on the human brain, just to touch the surface of it, we call ECOG. But most safe one will be obviously non-invasive. Just put on the scalp. So I somehow, as an engineer, I involved in that those aspects of the making the BCI from the fully implantable and then also the non-invasive one. So I'll talk about the my lab's work and also collaborative work in that area, so that we can create this kind of a feedback, and I'll give you some hint of that, what we do, and to make this signal processing and generating the commands, and so that we can have this control the closed loop feedback. So let's talk about the invasive BCI. As I mentioned to you, Utah array has the about, for example, 64 and the needles, and then you find the specific area, and then you plug in, and you have all the 64 channels will be received through the amplifier, and then that will be sent to either wire or wireless. Of course, wireless will be good, because the wire is that you have the wire from your brain to the computer connected in the wire. That will be tough, right? But the experiments is wired because of the informations that you send, and a 60-foot channel, and also getting the, for example, 2,000 data points per second per channel. That's a lot of data, right? Sending all wirelessly is tough. So many cases is wired. I'll talk about the wireless case, and that we do in our lab. This is good because it's accurate, and you can actually have the accurate pin, usually silicon coated with the gold, can touch the one specific neurons that we want to sense it. So you can have a very accurate, digitized the pulse, and based on that. So for very accurate, the control, the BCI, this is the only way to do. But has a lot of issues. It's risky. It damages the brain, and also the accuracy fades over the time because of many things, including the foreign objects. So that human has the defense system, and then foreign material will stick to the electrode and either change the conductivity of it. But regardless, and that's the probably the most advanced the way to make a most complicated the control that human does very easily. For example, just moving just a robotic arm, and with that bicep, tricep, and some of the fingers, it takes a tremendous amount of the data to do. So how they do? And they put not just one electrode array, multiple. So it gets not 64, it gets far more than that, several hundred. The array will get it, will go to the signal processing. Eventually, it will use that special technique, such as the pattern recognition, machine learning, and then understand the intention of the brain, and based on that, it generates the the control commands to move the motor of shoulder, elbow, wrist, or even fingers. And it depends upon the number of the channels of the actuation will be more difficult again. And then you can have that motion. And usually the eye will be the good and the feedback. Also, if you have that some touch sensors on the robotic fingers, even you can have that some of the tactile feedback directly back to the the brain too. Okay. Success story, and 90% of them use monkeys. Okay? So why is that? The monkey is again, and you can open the what? And the monkey's brain. And it is not 100% the same, but similar. So this is the one case of it. You see that here, actually the monkey's brain is open. And it has the invasive, the electrode connected to the computer. This is a robotic arm. And as you see, the monkey actually can control the robotic arm to eat the banana, right? So that's so this will be the, for example, the prosthetic, hand control, and it shows that. Rarely we see the successful story from the human subjects, and Boston University, Massachusetts, and Pittsburgh, and there are several the famous and the labs that they conducted the similar experiments on human. So this one shows that the patients actually eat the chocolate, right? And using the robotic arm, and she's completely paralyzed. So, but you see it, she has what? BCI and actually the electrodes in the brain. So we see that some the success story. We do this, and through the collaborative work with the NSF funded the projects, so-called CSN, long name, Sensory Motor Neural Engineering, with the University of Washington, and the MIT and the SDSU. We've been doing this one for last 6 years, and this is my part of the work, and making a coin-size, fully implantable, and brain-computer interface. So this was the design about 5 years ago, and we've been spending a lot of money, a lot of engineers, and to make this device. And then so we, they were able to, to make it, and then we are in the stage of, the testing. Okay. So, for example, let me give you that just what involves the reading the, the brain signal, and the providing the information, the to compute and in the computer. Okay. So this one is one of the circular chip we have developed, and has that the analog to the digital the converter and the amplifier with a multiple electrode, and then we have the onboard computing for the signal processing, and then we have the wireless. We are using the Bluetooth and through the antenna, so that actually the data can be transmitted through the skull without the wire. Okay? So this is the one of the chips that we have put into a circuit. So if we get into a little bit detail, then one part of the device is that specially designed rechargeable battery. So this is the fully encapsulated for the medical implantable purpose. So they made it Root-J, the company, just for this research. So this is only one kind of the special battery. And we spent a lot of time in the ETRI, one of the